Hello children, in thermodynamics, we were doing different types of enthalpies of reaction. We discussed about enthalpy of reaction, standard enthalpy of reaction, then we talked about enthalpy of formation, enthalpy of phase transformation. All these things we already covered till enthalpy of formation. Now in this lecture, we will be discussing about some more different kinds of enthalpies. So let us start with enthalpy of combustion. Enthalpy of combustion. We represent it with the symbol delta HC. Definition is very simple as we defined all other previous enthalpies. Similarly, we begin in this case. Like enthalpy of combustion is the amount of heat change when 1 mole of a substance is completely burnt in presence of oxygen. Understood? Amount of heat change when 1 mole of a substance is completely burnt in presence of oxygen. That is termed as enthalpy of combustion. For example, if I am writing combustion of carbon. So how do we write the equation? Combustion means the reaction with oxygen C plus O2 gives CO2. During this process, the amount of heat change is termed as enthalpy of combustion. Now write the physical state. Carbon is solid, oxygen gas, CO2 is gas. So this is the meaning by enthalpy of combustion. And as we know, combustion is an exothermic process. So enthalpy of combustion is always negative. Because we discussed in previous lectures also, for endothermic it is positive, for exothermic it is negative. After this, the next definition is enthalpy of atomization. Enthalpy of atomization. Now, how do we define enthalpy of atomization? Enthalpy of atomization is the amount of heat change when 1 mole of a substance is converted into its atomic and gaseous state. I am repeating it. Amount of heat change when 1 mole of a substance is converted into its atomic and gaseous state. That is termed as enthalpy of atomization. For example, if I take methane. So how do I represent enthalpy of atomization? It will break into atomic as well as gaseous state. That is termed as enthalpy of atomization. Now balance it. 4H. Enthalpy change during this process is termed as enthalpy of atomization. Or I may write Cl2 is converted into 2Cl. The enthalpy change during the process is termed as enthalpy of atomization. So children, I think now the meaning of enthalpy of atomization is, next we have definition of bond enthalpy. This is amount of heat required to break the bonds in 1 mole of a compound. Simple. Shall I repeat? Amount of heat required to break the bonds in 1 mole of a compound. That is termed as bond enthalpy. And with the help of bond enthalpy, we can easily calculate the value of enthalpy of reaction or heat of reaction. This is sum of bond enthalpy of reactants minus sum of bond enthalpy of products. So by using this equation, we can calculate heat of reaction. Sum of bond enthalpy of reactants minus sum of bond enthalpy of products. And in case of polyatomic molecules, in case of bond enthalpy, we always take the term average bond enthalpy. Now, what do we mean by average bond enthalpy and why do we take average bond enthalpy down? For example, if I am taking CCl4, carbon is bonded with 4 chlorine atoms. When I break first carbon-chlorine bond, I will left with CCl3 and chlorine is released. Then I have to break the second bond, then third bond and then fourth bond. And to break each bond, different amount of energy is required. That's why first we calculate each step enthalpy, means enthalpy required to break one after other bonds in CCl4. And finally we take the average of all these enthalpies, that will give us bond enthalpy for CCl4. The next term we use is lattice enthalpy. Remember this term, children? We already use this term in case of chemical bond chapter, right now? I think few of you must be remembering it, but okay, I'm telling you again what is lattice enthalpy. The basic difference in bond enthalpies, lattice enthalpy is this. Both are related with the breaking or formation of bonds. But this term is related with ionic compounds only. We use this term for ionic compounds, not for covalent compounds. So, the definition of lattice enthalpy is the amount of energy released during the formation of bonds in 1 mole of ionic compound. Amount of energy released during the formation of, released. If we are using the term formation, then use released. If you are using the term breaking, then use the term energy absorbed. Because formation is exothermic process and dissociation is endothermic process. So when I am saying amount of energy released means formation is taking place. So I am defining this, that amount of energy released during the formation of 1 mole of an ionic compound, that is termed as lattice enthalpy. Next topic is Hess law of constant heat summation. Now what is this Hess law of constant heat summation? By using this law, we can calculate the enthalpy of any given process. Now how do we calculate that? For example, I am converting A into B and I want to know how much heat change is taking place during this conversion. So how do we calculate that heat change? Suppose I am taking the change of enthalpy during the process is delta H. Now the complete conversion process is supposed in this way. First A is converting into B, B is converted into C, and then C is converted into D. Now let us take the enthalpy change for each step are delta H1, delta H2 and delta H3. So according to this Hess law, delta H is equal to the sum of enthalpy change of each step. Sum of enthalpy change of each step. So we may define it in this way that the total amount of enthalpy change always remains constant whether the process takes place in single step or multiple step. This is the one way to define Hess law. The total amount of heat change always remains same whether the process takes place in single step or multiple step. Or we can say the overall enthalpy change of a process is the sum of enthalpy change of individual steps. Dear children, I am repeating this definition further, that the overall enthalpy change of a process is the sum of enthalpy change of individual step. This is Hess law. Okay, now we are doing this question. The heat of formation of C2H6, CO2 and water. These three values are given to us. Now we are supposed to calculate the enthalpy of combustion of C2H6. Now children, in these type of case numericals, of enthalpy changes in thermodynamics, first of all, we are supposed to write the chemical equation of the given changes. Like in this case, enthalpy of formation of ethane is given. So first chemical equation we will be writing is for the formation of ethane. And if you remember the definition of enthalpy of formation we discussed, it is the amount of heat change when 1 mole of a substance is formed from its constituent elements. Remember? So it means the constituent elements of ethane are carbon and hydrogen. So first equation we will be writing on the basis of this, that is formation of ethane, C plus H2 gives you C2H6. Now balance this equation, 2 carbon and 3 hydrogen. Similarly write all other equations for these enthalpies which are given to us. The second enthalpy which is given to us is for the enthalpy of formation of CO2. CO2 means this is formed from carbon plus oxygen. These are the constituents of CO2. So again balance it. This is already balanced. And the third one is formation of water. The constituents are H2 plus O2 gives H2. Then balance it. This is balanced by half mole of oxygen. In this way write all chemical equations. Once all the equations written, balance them. After balancing, write the physical states also, carbon solid, hydrogen gas. In this way write the physical states for all these components. Then substitute the values for enthalpy changes for each case. Enthalpy of formation of C2H6, delta H formation for C2H6, this is delta H formation for CO2, this is delta H formation for water. Write all the values here, these are given. Let I'm assuming this is A, B and C. Using these terms here, A, B, and I'm taking this as C. So this is minus A, B and C all in kilojoule per mole. Then children, this is the first step. We have written all these 3 equations. Now after writing all these 3 equations, we are supposed to write the required chemical equation. From all these, what we are supposed to calculate enthalpy of combustion of C2H6. Combustion, if you remember during definition, we talked, this is the amount of heat change when 1 mole of substance is completely burnt in presence of oxygen. So combustion means reaction of that substance with oxygen. So as this is combustion of ethane, so we write the equation for combustion of ethane. Now our required equation, that will be ethane with oxygen, and we know all hydrocarbons on complete combustion give CO2 and water. After writing the chemical change, again we will be balancing this equation. 2 carbon, multiply this by 3, hydrogen is balanced. Now just check how many oxygens are there. 4 plus 3, 7. So we write here 7 by 2 oxygen. Now physical state, gas and liquid. Correct? We want to calculate enthalpy of combustion for C2H6. This we have to find. This is our required equation. Now how do we go? We want to get enthalpy change for this equation by using all these 3 equations. Now whether you add these equations, subtract, whatever you do, just check to get this equation. Now how do we go further? See, in this equation for reactants we need ethane and oxygen. In these 3 given equations, check first equation is giving us the value of ethane. But in first equation, ethane is towards right side, means product side, but we need ethane towards left side, means its sign is going to be changed. Got it? Then as a product, we need CO2 and water. See, the second equation gives us the value of CO2. Third equation is giving us water. But now check the number of moles, 2 moles of CO2 we need. So we multiply the equation second by 2. Because we need 2 moles of CO2 and in second this is 1 mole of CO2. Now how many moles of water we need? We need 3 moles of water. But in this equation you have only 1 mole of water. So multiply this equation by 3 to get the number of moles of water. So in both cases CO2 and water are towards product side. We also need CO2 and water towards product side. It means we will be adding equation second and third, and from this sum subtract equation first. Understood? Add equation second and third by multiplying with 2 and 3 and then subtract the equation first. You will get your desired equation. So what is our answer? What we will be doing? Equation 2, twice of equation 2 plus thrice of equation 3. From this sum subtract equation 1. You will get the enthalpy change for this given equation. So substitute the values here. How much heat is released in second equation? Minus B. Take the value of B from here. This is B now. So in case of second, the heat is twice of minus B kilojoule per mole. Then for third, amount of heat is C. Multiply this by 3. So 3 times of this heat. From this sum, subtract the enthalpy change for equation 1, that is A. Solve it, you will get answer for the enthalpy of formation of ethane, and that is required. Yes children, next question based on the same concept. In this case given is calculate enthalpy of formation of methane. So just start writing the chemical equations. We are supposed to calculate enthalpy of formation of methane. Means the first equation we will be writing is for the formation of methane. And the constituent elements of methane are carbon plus hydrogen gives you CH4. For this delta H formation for CH4 we have to calculate. Now balance this equation 2H2 and write the physical states also. For this we are supposed to calculate the enthalpy change. Now write the given enthalpies, equations for all given enthalpies. Given is combustion of carbon, hydrogen and methane. It means now we are supposed to write the equation for combustion of all these components. Combustion means reaction with oxygen. So C plus O2 is giving you CO2. Again I am taking them as enthalpies are as A, B and C. Then you will substitute the values from there. So C plus O2 CO2 already balanced. Physical states. And then take the value of delta H, that is minus A kilojoule per mole. Then second equation for the combustion of hydrogen, that is H2 plus O2 giving you water. Now physical state and balancing. Delta H, I am taking this as B kilojoule per mole. Third is combustion of methane, that is CH4 plus oxygen, and all hydrocarbon on complete combustion gives CO2 and water. Now we write here physical states already written. Now just check balancing of equation. 1 carbon already balanced, 4 hydrogen, multiply this by 2, hydrogen is balanced. Now check how many oxygen right side, 2 plus 2 4, so we multiply this by 2, balanced. Now write enthalpy change delta H, that is minus C. C kilojoule per mole. So all these values are given to us. We have written the equations for given enthalpies. Now again, as we did in previous case, we have to use these chemical equations to get a required equation. As I told you earlier, in the similar way, start. I hope you can easily do. Okay, do it with me, then you try a few more questions. Like here, as a reactant, I need carbon and hydrogen. So children, please check which equations give me the value for carbon and hydrogen. In equation, let us, this is I'm taking as equation 1. This one is 2 and this one is 3. So first equation will give me the value of carbon. Then check the number of moles. How many moles? 1 mole I need, and here also 1. No change is required. Second equation gives me value for hydrogen. But I need 2 moles of hydrogen, and in this equation there is 1 mole of hydrogen. So before adding first and second, I need to multiply equation 2 by 2 so that I will get 2 moles of hydrogen. So you multiply this second equation by 2. Then we add first and second. It will give us value of C plus 2H2. So the first statement is equation 1 plus twice of equation 2. If we are doing this much, we will get the value of reactants. Now check product side. Product side we are having methane gas. Check which equation gives us the value for methane. It is in third equation. Once we see that which equation give us a required component. Once we check that, then you check the direction, whether the component is present on the same side where we need it or this is present towards opposite. Then we check the number of moles. So in this case I need 1 mole of methane. Here also I am getting 1 mole of methane. So number of moles is same, but the side is different. I need methane towards product side and here methane is towards reactant side. So simple, I multiply this third equation from the sum of first and twice of second. If I do this, I will get my desired equation minus equation third. Simply, you will get the value for your required equation. Substitute enthalpies here. The enthalpy change for first equation, I have taken minus A plus second equation minus B, twice of minus B, and then from the sum, enthalpy for third equation is minus C. Now substitute the values of A, B and C from the question and solve it. You will get the answer for enthalpy of formation of methane. Yes children, our next question is based on bond enthalpy. I think you all remember the definition of bond enthalpy. Right now we discussed. Few topics ago we discussed this now. So just read the question what is given and then we start in the similar way as we tried the previous questions. Given us is bond dissociation enthalpy for hydrogen, chlorine is Cl2 and HCl. So bond enthalpy for H2 is given, bond enthalpy for Cl2 is given and bond enthalpy for HCl is given. All these three values are given to us. Similarly, I am taking them as A, B and C. So this is A, this is B and this is C, all in kilojoule per mole. So these three enthalpies are given to me. Now I am supposed to calculate the enthalpy of formation of HCl, enthalpy of formation for HCl we have to calculate. So first write the chemical equation for the formation of HCl. Each substance is formed from its constituents only. So the constituent of HCl are hydrogen and chlorine. So obviously it is formed by reacting with hydrogen and chlorine. After writing the chemical equation, physical state, and then you balance the chemical equation balanced by half mole of hydrogen and half mole of chlorine. For this enthalpy change, we have to calculate. So this is very simple question, because in this case directly we will be using the formula which we discussed in case of bond enthalpy, that enthalpy of reaction is the sum of bond enthalpy for reactants minus sum of bond enthalpy for products. Check in this reaction, reactant hydrogen and chlorine are there, and in the form of product HCl is there. So this is enthalpy of reaction is bond enthalpy for hydrogen plus bond enthalpy for chlorine. Now how many mole of hydrogen are there? Half mole of hydrogen. So multiply this bond enthalpy by half. Similarly half mole of chlorine. So multiply this enthalpy also by half. Minus bond enthalpy for product. In the form of product I am having HCl. So bond enthalpy for HCl. All these three values are given in question. For hydrogen this is A, chlorine this is B, and HCl this is C. So this will give us answer half of bond enthalpy of hydrogen, that is A, plus half of bond enthalpy of chlorine, that is B, minus bond enthalpy of HCl, that is C. Substitute the values of A, B and C from this given equation and you will get the answer for enthalpy of formation of HCl. So with this we have completed first law of thermodynamics. And the definition of first law, if you remember, it was total amount of energy of universe always remain constant. Only exchange of energy takes place between system and surrounding, but the total amount of energy always remains conserved, constant. That's why the law is also termed as conservation of energy. So with this law is completed. Now in next video we will be talking about second law of thermodynamics. In second law of thermodynamics we talk about feasibility of a process, that whether under given sets of condition a particular process takes place or doesn't take place. And if a process is happening, then why it is happening, and if a process is not happening, then what are the reasons why under similar condition one process is happening and the second is not happening. Because first law doesn't give us any kind of information regarding the possibility of a process. It only talk about that if a process is taking place, then how much exchange of energy is taking place. But about the conditions or spontaneity of a process, this law is absolutely silent. So wait till next lecture. In next lecture, we will discuss all these things.